Alrighty, gang, welcome back. Today we're going to continue talking about improper integrals. Specifically, we're going to learn about type 2 integrals. Yeah, let's just get into it. I'll tell you at the outset here, we're not going to do a lab today. So after we finish the lecture, that will be the conclusion. I figure you guys all want your tests graded. I have not graded your tests. Some of them, but I have not finished grading your tests. So I imagine you guys would rather me spend that time grading than just talking more and more about improper integrals. This isn't a terribly hard section, and so I think it's not inappropriate to do that. Let's get over here. Finish up this section. So this is MAC2312.004. It's a lecture, and today is the 18th. Today, we're going to do more.
Professor, your camera's blurry.
Oh, okay, thank you. Proper integrals. Should start, come on. There we go. More improper integrals, which is section 7.8. All right, and that's it. That's the game. That's all we're going to do today is finish up section 7.8, and then we're going to call it. Last time we learned about type 1 improper integrals. Let's see, recall a type 1 improper integral is one of the form either integral a to infinity f of x dx or integral negative infinity to a f of x dx, where f is continuous on either, whichever interval you're talking about, a to infinity for 1 or negative infinity to a for 2. All right. And each of these, this is 2. Each of these is defined to be a limit, right? Lim r to infinity, integral a to r, or lim r to negative infinity, integral r to a. So the idea is if the function of f is continuous on the interval either a to infinity or negative infinity to a, if the function f is continuous over this range of x values, then the reason the integral is weird is because the region is infinitely wide. And so there's this question of whether or not that area is finite or infinite. A type 2 integral is one where the region is infinitely tall. So another way integrals can be improper is if the region whose area is being measured is infinitely tall. All right, so this, let me put a little divider here. This is the end of what type 1 improper integrals are. So what we want to look at today is type 2 improper integrals. And an example, a kind of intro example here, a place where the integral is improper because the region is infinitely tall, would be something like integral 0 to infinity 1, actually, sorry, let me do integral 0 to 1 of integral 1 over x dx. You know what the graph of 1 over x looks like. Hopefully. You certainly should know what the graph of 1 over x looks like. It looks like this. And so what we're asking for here, if this is 1, what we're asking for here is the area going all the way up here. And this certainly could be infinite, right? Because this region here is infinitely tall. The way it turns out we handle this is similar to the way we handle type 1 integrals. The problem spot here is at 0. So if between 0 and 1, I chop like this, I can find a formula for the area in this region over here from like 1 between r and 1. And then I can send r towards 0. So that's the game. We define this to be limit as r goes to 0, integral r to 1 over x dx. Now there's a small catch here. If you're looking at this picture, I want to send r to 0, but I'm sending r to 0 from the right. I'm not interested in r coming in from the left because that doesn't have anything to do with this region. So the only thing that's a little bit trickier about the type 2 integrals, you got to take these one-sided limits. You got to be a little bit careful. Okay. If you want to see in Desmos, one over x. And so the region we're really looking at here is 0 less than y less than 1 over x, where it's this region, right? And clearly this region is infinitely tall because 1 over x, you know, blows up to infinity at 0. And if you kind of turn your head sideways, it looks a lot like the type 2 integrals. Yeah, very similar, right? So the question is, well, is this area finite or infinite? It's really the same problem, it's just like rotated. So, no, whatever. So let's crunch it out. Let's see what we get. So this should be equal to the limit as r goes to 0 from the right of an antiderivative for 1 over x. That's ln absolute value of x. And I have to evaluate this between bounds. So that's going to be lim r to 0 from the right, the natural log of 1 minus the natural log of r. And again, I'm losing the absolute values here because 1 is positive, r is going to 0 from the right. So it's understood that r is positive also. What's the natural log of 1?
0.
0, good. So this is 0 minus the natural log of r. So what I need here is lim r to 0 plus 0 minus the natural log of r. Now let's see who knows the graph of the natural log function. What does ln of r do as r goes to 0 from the right?
Decreases, goes to negative infinity.
Good, yeah, negative infinity, right? Negative infinity is that limit. So if you want to, we can separately sort of here's the log function, right? And as we go to 0, he's diving down to negative infinity. He just keeps going and going and going. So the limit in question here, as r goes to 0 from the right, the natural log is rapidly diving down to negative infinity. So this is 0 minus negative infinity, which is positive infinity. So the area in question, this area, is positive infinity. In other words, the integral diverges. The rule for convergence and divergence with type 2 integrals is the same as for type 1 integrals. It's the same for all improper integrals. If the limit exists and is finite, we say the integral converges. If the limit fails to exist or is not finite, then we say the integral diverges. And that should sit well with our kind of general notion of convergence. An infinite process is said to converge if it leads to a finite, definite thing, and said to diverge otherwise.
It's the only time where we know whether it's convergent or divergent at the very end,
Yes.
or is there
Exactly.
somewhere in between where we can tell?
Well, it depends. So there's a specific theorem or two I'm going to show you at the end of class today that will give you some tools that will allow you to deduce whether an integral is convergent or divergent, but only in special cases. So the vast majority of the time, you will have to crunch out the integral. Really, the special step is being able to get to the antiderivative, right? Once you have a formula for the area from r to 1, then you're in really good shape. That's this, right? The area from r to 1 is the negative natural log of r. And then we can just send our limit. But yeah, there will be some tricks down the road that I can show you to speed things up. But for the most part, you should be ready and happy to crunch out the integrals. The types of problems we're going to solve down the road are going to be much, much harder. So we're actually very lucky in the setting of improper integrals that we can solve them instead of having to work hard to figure out indirectly whether they're convergent or divergent. When it comes to infinite series, we'll have to work indirectly most of the time. Let's look at a couple other type 2 integrals. I'll look at one or two more examples here, and then I'll give you the sort of formal definition, and then I'll show you those theorems. So we saw that the integral of 1 over x from 0 to 1 diverged. Let's find something else that's a little bit fun. Yeah, okay, so discontinuous, these are these guys. Yeah, fuck it, let's do this. So one of the sneaky things about type 2 integrals is that they don't always immediately look improper, right? Type 1 integral has a little giveaway. It's got that infinity as a bound, but a type 2 integral can look very innocuous, like integral 2 to 3, 1 over the square root of x minus 2. You could hand this to a Calc 1 student and they would start grinding away on it without even realizing that it's improper, but it is. Because this function is discontinuous at 2. Right? If you plug in x equals 2 here, this piece is 0. So you're talking about 1 over the square root of 0. Well, that's 1 over 0. That's undefined. The graph of this is, again, something that you should know. Let me just do it like this. I can change things. There we go. So this is 1 over root x, right? So if I have 1 over root x minus 2, that just moves everything to the left. And then I'm interested now from 2 to 3. So here's the area I'm trying to figure out. I want to know, is this finite or infinite? This is an improper integral, and the problem is at the lower bound again. Problem could be at the lower bound, could be at the upper bound, could even be somewhere in between. So I have to set this up as a limit. This will be the limit as r goes to 2 from the right, integral r to 3, 1 over the square root of x minus 2 dx. Does everybody see that? So I gotta think of r as being somewhere between 2 and 3. And then I'm gonna find the area from r to 3, and then I'm gonna let r sneak up on this problem point. Sort of the picture here, I'll do my best to draw one by hand. We have a vertical asymptote at x equals 2. And then the function kind of looks like this. So over here would be 3. So the area I'm looking for is all of this area. And the way we get at it is by dropping r in here between 2 and 3. And then finding the area from r to 3 as a function of r. And then sending r back towards 2. Now, how do we actually compute this integral? Well, the antiderivative here isn't bad. It's going to be a little u sub. I'd write this as lim r to 2 plus integral r to 3 x minus 2 to the negative 1/2 dx. And then I make a little substitution. I'll let z be x minus 2 dz is dx. And it's important you write this as a limit before you do your substitution. Remember, all of the stuff that we have for our integrals only works for regular proper integrals. If you want to use a substitution or IBP or trig sub or anything on an improper integral, first you have to write it as a limit of proper integrals. So my bounds, my old bounds, were x equals r and x equals 3. When x is equal to r, z is going to be r minus 2. And when x is equal to 3, z is going to be 3 minus 2, which is 1. So I get lim r to 2 plus integral from r minus 2 up to 1 of z to the negative 1/2 power dz. dz is just dx. So I'll continue this over here. This is going to be lim r to 2 plus an antiderivative for z to the negative 1/2. Well, you add 1 to that power, you get positive 1/2. And then you divide by positive 1/2. That's the same as multiplying by 2. So we get 2 times the square root of z. And this is to be evaluated from r minus 2 up to 1. Which is lim. And I know that it's annoying, but you need to keep writing these limits. 2 times the square root of 1 minus 2 times the square root of r minus 2. Like that. Now the square root of 1 is 1, so this whole piece here is just 2. So this is lim r to 2 plus 2 minus 2 times the square root of r minus 2. So as r goes to 2 from the right, what does the square root of r minus 2 do? So we get to check how good your Calc 1 stuff is with your limits. Who can picture the graph of this function? Who sees it in their head already?
Is it like a ln function kind of, but 2 units to the right?
Sort of. It's not an ln though.
It looks like the ln.
Little bit, right? It's concave
Yeah.
down and increasing. In that sense, it looks like the natural log, but the natural log function like dives down, yeah? So this is a square root function. It's half of a sideways parabola. The other half looks like this. All right, if you turn your head sideways, that looks like x squared. Square root of x is half of a sideways parabola. So the thing in question here is the square root of x minus 2. So, minus 2. So it's been shifted to the left, or sorry, shifted to the right 2 units. So as r goes towards 2 from the right, the square root of r minus 2 is going to 0. In other words, this limit you can take just by plugging in. You get 2 minus 2 times the square root of 2 minus 2. Square root of 2 minus 2 is the square root of 0. So you get 2 minus 2 times the square root of 0. That's 2 minus 0, which is 2. So this integral converges to the value 2. In other words, the area here is finite. The area we were looking at originally here is finite.
Is it also correct to say if you like just write out the original integral and say equals 2, is that also correct or no?
That's correct, yeah. But you want to be careful. You want to make sure that you're saying it converges to 2. It is true that the value of this thing is 2. This is equal to 2. And that's why we've got like this is equal to, equal to, equal to, right? We've got this whole chain of equal signs. So yes, this integral is indeed equal to 2. But we want to make sure that we're also being clear. We're saying that this is a convergent integral and it is equal to 2. So the original question here is this area finite or infinite? This area is finite, even though it's infinitely tall. In other words, if you were to roll up all of this area, it's so narrow that if you were to roll it all up, it fits in a 2x1 box.
Is there a way to tell from just a graph if you don't have an equation? Okay.
Nope, there is not. I'm sorry. It would be nice, but there is not. Okay.
I have a question.
Yeah.
So like, you know how here we could just plug in what r is going to, like 2, we just plugged in 2. How come in the other one we couldn't just plug in 0?
Oh, because the limit there was a little bit more subtle than the limit here. So remember the rule from Calc 1 is you can take limits by plugging in. If we come back to chapter 2, section 2.5 on continuity, the definition of continuity is the limit is equal to the value of the function there. So it happened to be the case that this function, square root of r minus 2, is continuous at 0, or sorry, is continuous at 2. So we can take the limit here just by plugging in. But the previous function, ln of r, that's not continuous at 0. So there we had to think a little bit more carefully. But in both cases, we should be thinking about the graph, right? That's why I put up the graph of the square root function here. Really, in both cases, we should be thinking about this graph. So as we go towards 2 from the right, we're going to 0.
Okay. All right, thank you.
Yeah, of course. You can always try plugging in, right? But then if you get an expression that doesn't make sense, or you get something like 1 over 0, something that's undefined, then you have to look more carefully. And the natural log of 0 is undefined, so we have to look more carefully there. Other questions on this one? Okay. So let me grab a slightly more challenging problem, and then I'm gonna show you some theorems. Let's look at something that mixes together some of these challenges. So there, we're not doing this. There, we're skipping over 3/4. Do we not have any that mix these together? We might not. We might not. Okay. Then if we're going to keep these all nice and tame like that, I guess that's okay. Do not have anything weirder? Not really, shit. Okay, well, let me show you something here. What if I wanted to do the integral from 0 to infinity of 1 over x minus 1 quantity squared dx? Can you guys picture the graph of 1 over 1 x minus 1 quantity squared? We know what this looks like. This is undefined at x equals 1, right? And 1 is between 0 and infinity. So we're going to run into some type 2 problems here. But it's worse than that.
We can cut it into two different intervals from 0 to 1, and then from 1 to infinity.
Yeah, that's what we're going to have to do. So the integral, the graph of this function, rather, looks like this. It blows up at 1 on both sides. And we want to integrate all the way out to infinity. So we've got lots of problems here. The area we're trying to measure is the area of this region, which is infinitely tall, and the area of this region, and then we're going all the way out to infinity here, right? So this has lots of problems. I would begin by doing exactly what, I think it's Alexander who said that. We're going to split as integral 0 to 1 over x minus 2 squared dx, and then integral 1 to infinity, x minus 1 dx, and then integral from 1 to infinity, x minus 1 squared dx. But then this integral, the integral 1 to infinity, also has two different types of problems. So now this guy is, the first integral here is a regular type 2 integral. This integral has both type 1 and type 2 stuff. The second integral is type 2 stuff because of the infinite height over here, but it's also infinitely wide. So really we need to split this further. I'm going to continue down here. This would be integral 0 to 1 over x minus 1 squared dx, plus, now this guy I need to split up also. because I've got a problem at 1, and I also have to go all the way out to infinity. So I would call that maybe integral 1 to 2, 1 over x minus 1 squared dx. And then integral 2 to infinity. I chose 2 arbitrarily. We could have chosen something else, x minus 1 squared dx, like this. So now each of these only has one problem. This is type 2. This is type 2. And this is type 1. And each of them needs to get their own special treatment. So for that first integral, I'll call this R, and I'll calculate that first integral as the limit as R goes to 1 from the left, integral 0 to R. So this first integral right here, I write as lim R goes to 1 from the left, because now R is sneaking up on 1 from the left, integral 0 to R, 1 over x minus 1 squared dx, plus this other guy, he's going from 1 to 2, so let me mark 2 here. 2 would be like right here. We'll call this S. Remember, we have to use different variables for these. And then I'll calculate the integral from S to 2. That's the second guy. So this is limit as S goes to 1 from the right, integral S to 2 of 1 over x minus 1 squared dx. And then the third guy, I'll introduce a variable here, call it t. And we'll do him as integral 2 to t. And then I have to let t go to infinity. So this would be plus lim t to infinity, integral 2 to t, 1 over x minus 1 squared dx.
Do we always use capital letters for the limits?
You can use whatever you want. I like using capital letters, but if you wanted to use something else, you could. This is just the notation I like. It's going to connect to a notation I'm going to use down the road when we start talking about partial sums of infinite series. We'll also use a capital letter to denote the upper bound. Yeah, you can use smiley faces or soccer balls or spades, whatever symbol you want. The important thing is we see why this integral needs to be broken into 3 pieces. Does everybody see why this needs 3 pieces?
Can you explain that one more time, please?
So this integral has 3 problems. It has a problem at 1 that we have to approach from the left and the right separately. So let me come over to Desmos again and see if we can take a closer look here. And then we want to go from 0. All right. So here's my function. All right, here's this region in question. And the 3 issues, the 3 issues here come from sneaking up on this vertical asymptote from the left. There's a possibility that if I just look at the area here, this area could be infinite, right? Just that on its own could be infinite, because it's infinitely tall. And then also, this on its own could be infinite because it's infinitely tall. And then also, this on its own could be infinite because it's infinitely wide. So those are the three issues here. Is that making sense?
Yep.
I've got the issue to the left of the asymptote here, the issue to the right of the asymptote here, and then the issue of going on and on forever towards x equals positive infinity over there. So all three of those things could give us trouble. So we have to split it up and give each one its own separate limit. There's kind of what happens over here, what happens over here, and what happens as we go all the way out to infinity here. If any one of those were infinite, then the whole integral diverges. Remember, that's a rule we talked about last time. If any part of an improper integral diverges, then the whole improper integral diverges. I'll tell you guys right now, this one converges. This one right here is finite. These two both diverge. These two are both infinite. Let's compute one of these two, and then we'll know that our integral is divergent because we'll have seen that one part of it is divergent.
If one of those integrals is it diverges, so the whole thing diverges.
Right, that's the rule. So we can remind us there. Recall, if any part of an improper integral diverges, then the whole improper integral diverges. So if any one of these were to diverge, then I would say that the original integral is divergent. So let's take a look just at this guy. He on his own is lim r to 1 from the left, integral 0 to r of x minus 1 to the negative 2 dx. You make a little substitution. C equals x minus 2. dz is dx. X is equal to 0. X is equal to r. When x is equal to 0, x minus 1. I don't know why I keep writing 2's there. Yeah, this is x minus 1. I'm sorry. When x is equal to 0, z is equal to 0 minus 1, which is negative 1. And when x is equal to r, z is equal to r minus 1. So this gives me lim.
Mira, tú te llevaste el cargador de la
Sí,
aspiradora.
yo te iba a decir que lo había dejado.
So this gives us lim r to 1, integral now from negative 1 to r minus 1. And then in here, I just have z to the negative 2 dz. An antiderivative for z to the negative 2 is negative z to the negative 1. And so I need to evaluate that from negative 1 up to r minus 1. Back in page 2. So what is this? Negative z to the negative 1. That's negative 1 over z. So this is lim. R goes to 1 from the left. Negative 1 over r minus 1 minus (-1 over (-1). Lots of minus signs here to get confused about. So this is lim r goes to 1 from the left, (-1 over r minus 1. That's what we get when we plug in the upper bound. And then minus 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 makes minus. You guys see where this is coming from, right? Because this is lim r to 1 minus (-1 over z, evaluated from (-1 to r minus 1). So when I plug in r minus 1 for z, I get (-1 over r minus 1, that's this. When I plug in (-1 for z, I get (-1 over (-1), but then I'm also subtracting that. So like this is positive, but then the minus here makes this minus. Who knows what the graph of this function looks like? All right, limits are all about graphs.
It's like 1 over x, but like reflected over the x-axis and shifted 1 to the right.
Perfect. Yeah, this is like 1 over x, shifted 1 to the right, that's the r minus 1, and then flipped vertically over the x-axis. So what is that? It's this. And we're sneaking up on x equals 1. And we're doing it from the left. So as x goes to 1 from the left, (-1 over r minus 1 or (-1 over x minus 1) is going to plus infinity. So this is positive infinity minus 1, which is still positive infinity. So the integral from 0 to 1 of 1 over x minus 1 quantity squared dx diverges. Therefore, the whole integral 0 to infinity 1 over x minus 1 squared dx must diverge. Right, and it's very important that we're careful with our language here. We want to make clear what we're saying. We're saying, okay, I computed one part of this integral. That one part of this integral was divergent. Therefore, the whole integral is divergent, right? Because we split this up into 3 pieces. That's how we got started here.
Okay, before we move on, plugging in the limit of r approaching 1 from the left, how did you get infinity from that?
Well, I was thinking about the graph, right? Here's the graph of 1 over, if you want to write it as r, we can do that. I'm just going to say y equals, right? Here's the graph, y equals (-1 over r minus 1. And as r goes to 1 from the left, this graph is blowing up.
So
To do this, if you want to, we can talk a little bit more about that limit. Another way to think of this limit
yeah, I guess it does matter in the situation that it's approaching it from the left.
It does. Yeah, the one-sided limits matter here. They really do.
Yeah.
So as r goes to 1 from the left, what is r minus 1 doing? Forget about the whole fraction. What about just r minus 1? So if I take
Let's just think about it as like 0.9 and then working upwards from that. Like it increases drastically the further you go.
That's the idea. Yeah.
Okay.
If I imagine r is a small, a number very, very close to 1, but slightly to the left of 1, then r minus 1 will be very, very close to 0, but it will be negative. So this is like (-1 over something very close to 0, but negative. And one way of writing that is this, right? Writing the 0 with a little minus here is like, yeah, okay, this piece is going to 0, and it's doing it in a negative way. And so you've got like -1 over -0, and that would give us plus infinity. This is something I've seen people do in Calc 1, and if it makes you feel a little more comfy, I think that's fine.
Okay, cool. Interesting.
Knowing the graphs is the real key here. Other questions or comments on this problem?
Just by knowing that one of the integrals is divergent, you don't have to finish the whole thing.
Correct.
You would just write on the test like it diverges.
I
Well, you
would
would read
say
that explanation.
specifically
the whole
this.
explanation,
Yeah, I would say, so I computed this integral, this part of my problem, which is this integral. I found that that is divergent. Therefore, the whole integral must diverge. We're employing there this rule. If any part of the improper integral diverges, the whole integral diverges. So you might want to cite this rule, right? But yeah. The moral of this problem is that you got to be comfy looking for all the issues with an integral, right? This guy had 3 different problems. Problem at the plus infinity and a problem on both sides of 1. So you got to get comfy looking out for those things. And then if you suspect that one part of those is going to be divergent, compute that part first. Because if it is divergent, then you can save yourself having to do any more computation. All right. So that's type 2 integrals and a mixture of type 1 and type 2 integrals. I have now for you some theorems. You remember at the end of class last time, I asked you to think about a tipping point for type 1 integrals. Specifically type 1 integrals of the form, sorry, not greater than 0, greater than 1. Integrals of the form like this, right? Or like 1 over x squared, 1 over x cubed, 1 over x to the 4, 5, 6, 7, 8. They all kind of look the same. What about 1 over x to the 0.5, or 0.25? So we made the observation, or we did the calculation last time to show that the integral that's on the page now is divergent, right? We saw that. We saw the integral of 1 over x from 1 to infinity. This is a divergent integral. And we noted that like 1 over x squared lives beneath that. All right, so like the purple function, and let me change, yeah, the purple function here sits underneath the blue function. So the purple area here the black area is smaller than the blue area. We know the blue area is infinite. We know the black area is finite. And the question becomes, well, functions like this, 1 over x to some power, when do those integrals come out finite? And when do those integrals come out infinite if we just integrate from like 1 to infinity? Let's come over here. Integrals of the form integral 1 to infinity 1 over x to the p dx are called p integrals. They're all type 2, or sorry, they're all type 1. These are a special family of type 1 improper integrals, about which we know everything. What I mean by that is I can tell you exactly for what values of P these converge and exactly for what values of P these diverge. I'll give you the theorem and then we'll prove it. Theorem. P integrals converge if P is strictly larger than 1 and diverge if P is less than or equal to 1. Note that it has to be a type 2 integral, right? We're not going over 0 here. We're integrating from 1 to infinity. That's important. These are just type 1. And the integrand has to be exactly this, 1 over x to some power. Anything else and it's not a P integral.
Does it matter the power is an integer?
Nope. Yeah, power does not need to be an integer. It can be anything. But oftentimes we first play with these with integer powers.
Would it be like, could the power be negative? No, right? Because it was sent to the top, right? Yeah. I remember.
Well, I mean, yeah, the power can be negative. It still fits into the scheme. A negative number is certainly a number that's less than or equal to 1. So I claim for any negative power, you'll have a divergent integral.
Okay. Wouldn't that basically be a polynomial?
Well, yeah, I mean, like, yes, but only with one term.
Okay.
Like the integral from 1 to infinity of x squared is included in this because that's 1 over x to the negative 2. And negative 2 is less than or equal to 1. So that would be a divergent integral.
Okay.
So let's look at the proof. If P is equal to 1, then we've seen that the integral is 1 to infinity 1 over x dx, which we've seen we've already done. We know that this diverges. We've shown this integral to diverge. We did this as one of our, I think, our very first example on Tuesday. If P is, let's say, we'll do this one first. If P is less than or equal to 1, then 1 over x to the P is actually bigger than 1 over x. Bigger than or equal to. So the integral from 1 to infinity of 1 over x to the P dx would be greater than or equal to the integral from 1 to infinity of 1 over x dx, right? If this function is bigger than that function, then the area under this function is bigger than the area under that function. But we know that the area under 1 over x from 1 to infinity is infinity. So our integral, the integral from 1 to infinity of 1 over x to the P dx, is bigger than or equal to infinity. So integral 1 to infinity 1 over x to the P dx equals infinity. And therefore diverges. Right? So think about this carefully. If the power P is less than 1, then x to the P is smaller than x. Let me show you what I'm talking about here. This is like what we're talking about. Let me look at some simpler cases. So here's 1 over x to the 0.1234. Oh, sorry, 0.1234. Right? So the blue function is bigger than the red function because the power here is smaller than the power here. Even if the power here is just a little bit smaller, you'll see the blue is above the red. And you know that the area under the red the area here, the green area, I'll change it to be red. You know that the red area here is infinite. So if the blue is bigger than the red, then the area under the blue is bigger than the area under the red. So the area under the blue has to also be infinite, all right? So far we know if p is equal to 1, the integral diverges. If p is less than or equal to 1, then the integral is bigger than the integral of 1 over x and must therefore diverge. The last case where we actually have to do some work is if p is greater than 1. If p is greater than 1, then integral 1 to infinity 1 over x to the p dx, we have to actually compute this, is lim r to infinity integral 1 to r 1 over x to the p dx, which is lim r to infinity integral 1 to r x to the negative p dx. Now we're ready for our antiderivative. We have lim r to infinity. I'll write it in the silly way first. This is x to the negative p plus 1 divided by negative p plus 1, evaluated from 1 to r. All right, this is a power rule thing. Yeah, just x to some power. Since I know that the power is bigger than 1, I'm not worried about the weird case where you get a natural log. Every other power rule integral goes just like this. So what does this thing look like? This is lim r to infinity. I can pop out a 1 over 1 minus p. That's the p minus 1 downstairs. He can come out. And then in here, I still have x to the negative p plus 1 evaluated from 1 to r. Now, since p is bigger than 1, negative p plus 1 really is negative. So I have 1 over 1 minus p here. And this piece is really 1 over x raised to the p minus 1 like this. Since p is bigger than 1, we know negative p plus 1 is less than 0. Because p is bigger than 1, right? So the negative of p is more negative than negative 1, which means negative p plus 1 is smaller than 0. So this term, this is really x raised to some negative power. I should put it downstairs. And I'm still evaluating here from 1 to r. So this is lim r to infinity 1 over 1 minus p times 1 over r to the p minus 1 minus 1 over 1 to the p minus 1. This piece right here is just 1, right? The whole piece there. 1 raised to the power p minus 1, that's 1 to a constant power. 1 divided by 1 is 1. The other piece we have to think about a little bit. What does this piece do as r goes to infinity? What does this do as r gets bigger and bigger and bigger? Looking for some love here. Help me out, guys. What's this piece do? Take some examples, right? If P is 2 or 3 or 4, then P minus 1 is 1 or 2 or 3. So what does 1 over x squared, 1 over x cubed, 1 over x, what do those do as their bottom goes to infinity?
Become smaller.
Do they go to 0?
Yeah. Yeah, this piece is going to go to 0. This is like 1 over 1 minus p times 1 over infinity to the p minus 1 minus 1. Well, you raise infinity to any positive power, and you're going to get infinity. So this is 1 over p minus 1. Oh, sorry, 1 minus p. Oh, damn it. Do it down here. 1 over 1 minus p times 1 over infinity minus 1. And 1 over infinity is 0. So this is 1 over 1 minus p times 0 minus 1, which is negative 1 over 1 minus p, which you could write as 1 over p minus 1 if you want. So that's the game. Specifically, this is a finite limit, right? P is strictly larger than 1. So that denominator is definitely not 0. This is a positive number downstairs. So 1 divided by a positive number, that's a finite positive number. So if p is bigger than 1, then integral 1 to infinity 1 over x to the p dx converges to 1 over p minus 1. Specifically converges. And that's the end of the proof. So this is something you need to remember. This is important. And I want you guys to do me a favor. In your notebook, I want you to set aside a few pages, like 3-4 pages, where you can put your convergence theorems, your convergence results. Leave them blank for now, right? But set them aside. Put a little sticky tab there or something so you can flip back to them often. The first thing you're going to put on those blank pages is just the statement of this theorem, right? P integrals, which are integrals of this form, converge if P is greater than 1 and diverge if P is less than or equal to 1. In fact, let me give you a nice, clear way you can get it in one line where you don't need anything else floating around. So convergence theorems for improper integrals. Theorem. P integrals, which are integrals of the form. Integral, really, it doesn't matter. It doesn't have to be 1. It can be any a to infinity 1 over x to the p dx, where a is a positive number converge if p is greater than 1 and diverge if p is less than or equal to 1. All right, this is your first theorem on convergence. And it's for improper integrals. Those 3 or 4 pages you're going to set aside for convergence theorems. The first page is going to be for improper integrals. The second page is going to be for sequences. The third page is going to be for series. We will have a collection of theorems for each of those things that you must know cold. Like, as well as you know your unit circle, hopefully, you must know these theorems by the time we get to exam 2. All right, so this is the first one. There's another one, and I'll prove this for you too. I'm going to prove it on a separate spot, but I might as well give it to you now while we're writing these things down. If 0 is less than or equal to f of x is less than or equal to g of x, then the integral from, I should say, and f and g are continuous on the interval a to infinity, then the integral from a to infinity of g of x dx converging implies that the integral from a to infinity of f of x dx converges. And integral a to infinity of f of x dx diverges implies that the integral from a to infinity of g of x dx diverges. This is called the comparison theorem. It says if one function is smaller than another function, and the integral of the big function is finite, then the integral of the small function has to be finite as well. And if the integral of the small function is infinite, then the integral of the big function is infinite as well. If you think about it, I actually used a special case of this theorem in the proof of this theorem when we talked about the p less than or equal to 1 case. So if you fit inside a finite box, you have to be finite. And if an infinite box fits inside you, you have to be infinite. That's the way to think about this second theorem. This is the version for type 1 integrals. There is a way to think about this for type 2 integrals also. The basic idea is just that integrals obey inequalities as long as there's no funny business going on. So here are your convergence theorems for improper integrals. You're going to have a page like this for sequences. It's going to have like 8 theorems. You're going to have a page like this for series. It's going to have like 7 theorems. And you need to know them all cold by the time we get to exam 2. All right, so let's leave this page alone. Make sure it stays nice and clean in your notes. You're going to flip back to it a whole bunch. And let's go elsewhere to solve some examples. And this will be the last thing we do today. After we do this example or 2 here, I'll let you go. How are we doing on time? We're doing good. All right. So, what's that? Oh, no kidding. All right. EG. Determine whether integral 1 to infinity sine squared x over x cubed dx converges or diverges. I'll tell you right now, if you can find the value of this integral for me exactly by writing as a limit and taking antiderivatives and stuff, I'll give you $1 million. Definitely give you an A in the class. There is no closed form antiderivative for this function. This is not an integral we can evaluate directly, not using any of the means that you would think. But we can use our comparison theorem. The comparison theorem is kind of like the squeeze theorem. You need to build up an inequality, right? Remember what the comparison theorem says. It starts out by saying if f and g are positive functions and f is smaller than g, then blah, 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 blah. So the function you're given here in this case is sine squared of x over x cubed. It's very hard to work with directly. So my solution here would look like this. Let's say, observe that for all x's greater than or equal to 1, 0, actually, let me even start further back. -1 is less than or equal to sine x is less than or equal to +1. This is always true of the sine function, right? Sine functions' outputs are always between -1 and 1. So 0 is less than or equal to sine squared of x is less than or equal to +1. Think about it for a minute. If you take numbers that are between -1 and 1 and you square them, all the negative shit becomes positive, but nothing ever gets bigger than 1. Or if you know what the graph of sine squared looks like, and maybe you should, but if you forget, there it is. You notice that it is bounded between 0 and 1, but you should be able to get there from here, right? You take all the numbers between -1 and 1 and square them, you get a bunch of numbers that are between 0 and 1. It's not like I squared each term here. -1 squared is not 0. I'm just applying some logic. Now, if I multiply through by 1 over x cubed, 0 over x cubed is still 0. I'll get sine squared of x over x cubed here, and 1 over x cubed here, giving us the inequality 0 is less than or equal to sine squared x over x cubed is less than or equal to 1 over x cubed. This procedure that I just went through to cook up this inequality, mega super double ultra fucking important. We're not just going to do this for improper integrals, we're going to do this with sequences and series as well. So you need to get good at building and working with inequalities. I can't stress that enough. Are there any questions about what I'm doing with the inequalities here, where it's coming from? Okay. Here's where my theorem is going to come in hand. So this period, right? We're working in full sentences. Observe that, blah, 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 so therefore giving us blah. The integral 1 to infinity 1 over x cubed dx on its own is a p integral. Right? Integral 1 to infinity 1 over x to the 3. That's a p integral with p equal to 3, which is bigger than 1. So integral 1 to infinity 1 over x cubed dx converges. Thus, let me give this inequality here a name. I'll call it star. Thus, by star and the comparison theorem, for improper integrals, what must be true? Well, this function is positive and smaller than this function. Also, the integral of this function is convergent. So if I am positive and smaller than a guy whose integral is convergent, my integral must also be convergent. That's the theorem. If the integral of the bigger guy converges, then the integral of the smaller guy converges. So by the comparison theorem for improper integrals, integral 1 to infinity sine squared x over x cubed dx must converge also. That's it, job done. You'll notice I don't have a fucking clue the value of that integral. I really don't. And I don't mean like I haven't just computed it here, I mean I straight up don't know. It's going to be very hard to get the exact value of this integral, extremely hard. But I know that it's finite. I know that this integral converges. And sometimes that's enough. Sometimes I'm just happy to say this thing is finite. That's all the problem here asked us to do, right? Determine whether or not this integral converges or diverges. That was the command given. And the tool we used to do it was the comparison theorem. So pay attention to the way this solution is worded. Pay attention to what we're doing. You're going to be writing a lot of things like this. Really what we're doing is writing these little proofs. They're little proofs, and we won't have to work from scratch most of the time. You'll be leaning on theorems that I give you. But you need to get good at wording these things, piecing together the little bits of logic. And it's not easy. I'm not going to pretend like it's easy. It's not. It requires you to think a lot. Yeah, sort of. We are going to, so this sort of procedure that we're doing here where we build an inequality and then make a comparison is very similar to something we do with series. And it's also true down the road that we will be making claims about series based on claims about integrals. If you want to read ahead, that will all be in chapter 11. 11.4 is a comparison test for series, which is very, very similar to the comparison test for integrals that we just learned. Where is it? It's in here. So, oh, I didn't see it. Where is it? That's the limit comparison test. Where's the, yeah, so this is similar, right? And B here's the positive terms. The way they phrase it here makes it a little bit more confusing. And then there's also something called the integral test. Don't stress about this for now. Just make sure you understand what's going on when it comes to the improper integrals. Understand this now, and you will understand the series stuff later. So here are the theorems we proved today. These integrals, P integrals, converge if P is bigger than 1 and diverge if P is less than or equal to 1. And here's our comparison theorem. F and G are continuous functions, one bigger than the next. They changed the labels here. I used F for the little guy and G for the big guy. But if the big integral converges, then the small integral has to converge. And if the small integral diverges, then the big integral has to diverge. So practice these problems. I put a few of these in your homework this week for you guys to work on. One of them is very, very similar to this. Another one is different. There's a way of thinking about these things as type 2 integrals also. There's a way of doing comparisons for type 2 integrals that I want you to figure out on your own. It's not that hard. It's the same sort of logic. If you're smaller than a convergent integral, you're convergent. If you're larger than a divergent integral, you're divergent. That is the basic idea that should be in your head. The big key is getting good at building inequalities, right? So arriving at this inequality by going through a sequence of steps like this. Questions on this? Alrighty, guys, I am going to go ahead and sign out here. There's not going to be a lab today. Please just work hard on the homework. I'll get your tests graded as soon as I possibly can. The goal is to get them all done today before the end of the day. And I will see you all next Tuesday when we're going to begin talking about sequences. And this is where the class starts to get hard. It changes. So if you've been kind of on the edge of putting in enough time, it's not going to be anywhere near enough time in the future. You need to really ramp things up. Yeah, Alejandro.
I didn't type the answers on the boxes on the test. I mean, I have the answers in the actual paper, but I don't know if they could be counted because I haven't typed them.
I'm not supposed to count them, but I will make an exception on exam 1 only. If you forgot to type your answers or didn't type them in, I will grade the written work, but only this one time. All right, I'm going to have to review the videos and make sure everything's kosher. But please, there's a very, very important reason why we need to type the answers during the test, so I can compare, what you type to what you write. Yeah, sorry, I guess I never gave the formal definition for a type 2 integral, did I? We just kind of did it by examples. Let me give the formal definition for a type 2 integral, and then we can go. So if f of x has an infinite discontinuity at x equals c, then the integral from c to b of f of x dx, this is defined to be the limit as r goes to c from the right, integral r to b, f of x dx, and the integral from a to c of f of x dx would be defined as the limit as r goes to c from the left, integral a to r, f of x dx. And we say that these integrals converge if the limit defining them is exists, I should say exists, and is finite. We say that these diverge if the limit defining them does not exist or is infinite. Yeah, so this is our formal definition of a type 2 integral. Yeah, sorry, so we did these by example and I didn't actually give you the formal definition. So the big thing is the infinite discontinuity, right? If you have an infinite discontinuity at one of the endpoints, then you have to set it up as a limit. And it just like the examples we did in class today. If you have an infinite discontinuity in the middle, we saw an example like that, you have to split it up and treat each side separately.
So will you always have like a limit R like going to C from the right and the left, or will it just depend on like where they give you the bounds? Kind of like that one problem.
Yeah, it depends. It depends. So this integral would be defined this way. This totally different integral would be defined this different way. All right, so it's not like these are the same integral, these are different integrals. I can show you like one or two quick setups here. Like the integral 0 to 1 of 1 over root x dx, I would set this up as lim r goes to 0 from the right of the integral r to 1 over root x dx. Or the integral from -3 to -2 of 1 over x plus 2 dx. This would be lim r goes to -2 from the left, integral -3 to r of 1 over x plus 2 dx. Okay, so I'm gonna go ahead and sign out here. I hope you guys have a good afternoon. Please work hard. I do have a normal office hour tomorrow if you want to come by and ask any questions. Grind on that homework and email me or come by office hours if you do run into anything where you're uncertain. Again, as you solve these, please try to write your solutions in full sentences, like we were doing in class today and Tuesday. It's important that you get comfortable doing that sort of thing, practicing the logic and being very careful with the words. That's the stuff that's actually really going to help you as we move into sequences and series. Also, try talking to each other about this stuff. Do you guys have a group me or a Discord or something for this class? Does anybody have something like that made?
Don't think so.
Not to the best of my knowledge, but that could just be a lack of inclusion. I'm not. We could
I'll
start
start
one.
yeah, I'll start a Discord server. And you
Yeah,
guys-
actually, that would be pretty neat.
I got you. Yeah, I'll get a Discord server set up and I'll post the link to the announcements in Canvas. Okay.
All right.
Professor, I
great
have two
day, Professor.
questions on the homework assignments. Can I just send you a picture?
Yeah,
Like
please.
if you
Yep,
can
that's
solve
perfect.
them and then I can just compare my work.
Yeah, send me a photo of your work. And if there's like a little mistake, I'll just type back a reply. If there's a big mistake, I'll give you a video or a picture answer.
All right, thank you so much.
Of course. Anything else driving us nuts before we go? Alrighty, guys. Have a good afternoon. Take care of yourselves over the weekend. I'll see you on Tuesday.
All right. Have a great day, Professor.